How did Earth receive its water? Learn now from reading Edinger journals. Currently, there is no accepted resolution for how our planet, Earth, received its water that is critical to giving birth to and sustaining life. A simple answer is not forthcoming from our astrophysicists and planetary scientists. If we tour the solar system as NASA has these past 50 or more years, we discover that the planets, moons, and minor planets between the Sun and the distance to the orbit of Jupiter, and our first gas giant, located at 5.5 astronomical units, are mostly bone dry. Why was Earth favored with liquid water orbiting at 1 astronomical unit, 93 million miles from the Sun? Even our nearest neighbor, the Moon, lacks hydrous qualities, which should be expected. The major accepted hypothesis for the formation of the Earth-Moon system is a collision that supposedly mixed the mantles of the two bodies, bringing any water that Earth had to the Moon. The predicted amount of Moon's water and any significant hydrated minerals cannot be found from the data analysis of NASA's Apollo missions. An important hypothesis is developed that the inner terrestrial planets lost all their gaseous volatiles that outgassed to their molten surfaces by severe solar winds and elevated surrounding temperatures of the forming protostar. A study of extrasolar stars, the size of our Sun, reveals a very hot, approximately 1,500 degrees Fahrenheit surrounding corona, reaching outward 2 or more astronomical units, called the T Tauri phase. These high temperatures can easily boil off or strip the lighter volatiles, including water, from nearby planets. Only their heavier rocky materials are left behind to form the terrestrial planets that eventually cool to make hard crustal surfaces with metallic cores. These planets' volatiles were carried away, possibly toward the frost line near 5 astronomical units, to form the giant gaseous planets of Jupiter and Saturn. The stripped materials from the inner solar system formed icy compounds of solids that were more abundant than the metals and silicates of the cores of the terrestrial planets. The abundance of these lighter volatiles allowed the outer planets to grow faster and capture hydrogen and helium, being carried away by solar winds. The frost line acted as a barrier to accelerate the accumulation of material about any forming planetary core beyond 5 astronomical units from the Sun. A triple-point phase diagram indicates the thermodynamic properties of water, depicting the conditions at the surface of the terrestrial planets. Mars is near the triple point where liquid water cannot exist due to very low atmospheric pressure. Earth is in the liquid region because it has enough atmospheric pressure and receives enough radiant energy, and is massive enough to retain its atmospheric constituents. And Venus is near the critical point where water becomes a very steamy vapor that can easily be lost to outer space. Venus's atmospheric elevated temperature above water's boiling point is not only due to its being closer to the Sun, but primarily due to its greenhouse gas of dense carbon dioxide. Earth's moon is assumed to reside in a similar earlier orbital position, as it currently does. A similar fate of its loss of atmosphere occurred due to its small size, just as Mercury, and experiencing the circumstellar temperatures of the Sun's T Tauri phase. In astronomy, the circumstellar habitable zone, or simply the habitable zone, HZ, is the range of orbits around a star, within which a planetary surface can support liquid water, given sufficient atmospheric pressure. The bounds of the HZ are based on the watery Earth's position in the solar system and the amount of radiant energy this region receives from the Sun. This zone reaches out to about the orbit of asteroid Ceres at 2.7 astronomical units and includes Mars at 1.5 astronomical units. The difficulty of water existing within any of these ranges is the required pressure and temperature combination produced by the type of atmosphere, the size or mass of the planetoid for holding on to the atmospheric gases, and the magnetic field surrounding such a body that protects solar winds from washing away the topmost atmospheric particles. Only Earth has these required features. The interesting fact is that Earth's first orbital location can only be the region within the range of the asteroid main belt which resides inside and near the edge of the proposed early HZ, where liquid water can exist if other conditions are met. An unanswerable mystery is created by Earth still possessing its water and other volatiles, such as nitrogen and methane, and surviving the T-Tauri phase. The same processes of atmospheric stripping of Mercury, Venus, possibly the Moon, and Mars should have occurred with Earth in its orbit between Venus and Mars. Astrophysicists first tried to resolve the mystery by imagining icy, watery comets or asteroids with a questionable delivery mechanism of their water from the outer solar system. After the hot T-Tauri phase, when the Sun became a stable, behaved main sequence star. But the space probes revealed that the hydrated minerals of comets have different water isotopes from Earth's oceans, and the newly suspected rocky chondrite asteroids, with their similar water isotopes, simply do not have significant amounts of water to supply the Earth's oceans. Space probe exploration of both asteroids and comets discovered that their compositions were very dry and mostly carbonaceous rocks. Instead of being hopefully dirty snowballs with much water, these rogue bodies were looking like the debris from the collisions of hard crustal surfaces, with most objects that were previously melted like igneous rocks on Earth. Similar water isotopes from asteroids and the Earth are easily predictable, since these asteroids are postulated to come from an impact with Earth. Possibly, collisions occurred in the outer solar system, where water could exist as hardened ice on the surfaces of smaller rogue planetoids, or planetary moons. But strangely enough, no outer solar system bodies have rocky crustal surfaces, except the collisional debris of asteroids. I can only predict a hypothesis, not yet fully explored by consensus science. Other specialized research continues to corroborate, but not entirely embrace, that Earth's water is due to originally being located close to the solar system's frost line, at 2.7 astronomical units from the Sun, and retaining its water in liquid form on a warm crustal surface during the T-Tauri transition. Then, planet Earth was struck and gorged by an icy rogue minor planet, like the moon Ganymede in size and composition, and displaced sunward to its existing orbit at 1 astronomical unit. This orbital transformation sets up a slow capture mode for the existing moon at 1 astronomical unit, with the impacted, displaced Earth with its water recondensing. Isotopic ratios of heavy, noble gases. Xenon is useful for showing the loss of water over time. Xenon is inert and is not removed by chemical reactions. Comparisons of abundances of its 9 stable isotopes in the current atmosphere reveal Earth lost at least 1 ocean of water early in the Hadean and Archean eons. This result aligns with Earth having a primordial ocean before its major impact and violently losing some liquid through vaporization into space. Mineralogical evidence in zircon crystals. The ages of Earth's zircon crystals establish that liquid water and atmosphere existed 4.404 billion years ago, very soon after the formation of Earth. This measured time presents a paradox of a cool Earth existing during the turmoil of its postulated formation by the accretion of large planetesimals and its birth location within the high temperatures of the pre-nebular disk of the T-Tauri phase. The paradox goes away if Earth is assumed to have previously formed with much less heat, from either accretion or by a binary mode, near a cooler orbital distance of about 2.7 astronomical units from the Sun. Delivery of ice-enriched bodies from beyond the frost line. The boundary where water-ice bodies could form in the early solar system is known as the frost line. This frost line is located about 2.7 to 3.1 astronomical units from the Sun. The feasibility of delivering enough of this ice water from that distance so early in the solar system's formation is doubtful. Both its timing and method of transportation cannot be easily explained, unless both Earth and its water were displaced from the frost line region 500 to 600 million years after its formation, due to a large impact or other means. The compelling evidence of a planetary body with a rocky, igneous crust covered with water and a CO2 atmosphere, located near the frost line at about 2.7 astronomical units, is a 4.6 billion-year-old meteorite that fell in northern Germany in 2019. This fallen asteroid contained carbonates that can only be created with the above-listed conditions near the early frost line. Lunar samples from Apollo missions 15, 16, and 17. The chemical compositions from lunar samples indicate that water was already present on Earth before the Moon was formed. This result corroborates that planet Earth was created before the Moon, with no need to have them be the same age, within millions of years, or involved in a collision model, as hypothesized by NASA. Also, from previous research, water existed on Earth very early, as long as 4.4 billion years ago, near the hypothesized solar system's formation that dictates the Earth's location at birth was located close and inside the frost line. Isotope differences between Earth's atmosphere and the mantle. Noble gas isotope ratios of Earth's oceans and mantle are different, suggesting different sources, such as either coming from a moon-forming impactor or the proposed impact at 2.7 astronomical units. The proposed impactor that embedded itself into the Earth's mantle and mixing the two mantles can explain the different sources. In conclusion, one should wholeheartedly accept this new proposal, called Earth's metamorphism, EMM, hypothesis. Planet Earth originally formed near 2.7 astronomical units from the Sun and avoided the extremely warm conditions of the proto-Sun's T-Tauri phase, unlike the other closer terrestrial planets. Still within the habitable zone, HZ, planet Earth quickly formed a CO2 atmosphere and liquid ocean on top of a very early differentiated hardened crust. The solar system had matured with the Sun, entering the main sequence of stars with a completed retinue of planets and with the sweeping away of most of its pre-solar dusty disks. The Earth's location gave some time to develop a thick crust and outgas and retain most of its lighter volatiles. Then, about 3.9 billion years ago, an icy impactor, like Ganymede, struck and penetrated Earth, bringing more lighter volatiles, including water. The first megacontinent on Earth was created from the huge impact crater to later provide the processes of plate tectonics and continental drift that are not found elsewhere. The energy from the impact mixed the two mantles internally, expanding and cracking the existing planetary crust. The resulting kinetic energy was also expended into tilting the planet's spin axis and displacing its orbit inward toward the Sun. As the gorged planet with its debris fell, its velocity increased until its centripetal force equaled the Sun's gravitational force. At that point, the Earth followed a new orbit close to the existing orbit of another terrestrial planet, now called the Moon. Earth's orbital velocity was slightly faster and passed the Moon on each orbit, thereby exchanging gravitational forces and angular momentum. The resulting unique capture mode slowed Earth to match the Moon's velocity and moved the Moon farther away. The shared orbits resulted in the Moon making a weaving synchronized orbit with Earth. Collisional debris either fell back to Earth or was swept up by the Moon, causing the craters we see and the mares of hardened volcanic lava, created by a continuing sweeping of minor asteroids that spanned 900 million years per radiometric data. The Moon eventually becomes tidally locked to the Earth. This transfigured Earth now receives greater light and radiant heat from the closer Sun, and a lesser reflected light and mild tidal acceleration from the Moon. The Moon is mistakenly identified as a satellite of Earth, but is really another planet, sharing the same orbit. Now you may know how the mysterious origin of Earth's water occurred, with some reasonable certainty. The only important water on the Moon or Mars will be brought there by humans. The only other large reservoir of liquid water that may be found in the solar system is by drilling through the icy crusts of some outer planetary moons. For further reading, consult with Edinger journals.